Yeah, all right. So let me directly jump into today's conversation. So this is the disclaimer for today. I don't want to proceed today's conversation in a lecture style. So this is really about the copy chat. So if you didn't bring any like the drink yet, please bring something. So I'd like to make today's like the conversation a bit casual. So one of the reason is that when I learn algebraic geometry from the same professor with Karen, so we learned 1 year like the coursework in graduate school, and we also did some like the seminar under the same professor. And the very first impression that we had together is horrible in terms of the amount of the necessary the knowledge. It was completely overwhelmed. How one can really catch up all those things in detail? I can study either the Harshon or the Rabi Bakr, all those kind of the text which is really thick. And oh God, how can this can be done? So, but I was very lucky that few projects I was able to catch up algebraic geometry in my own way. So I'd like to just share my very stupid inspiration that you completely can ignore, but hopefully this could be useful in a sense that I don't really feel overwhelmed with algebraic geometry and actually any algebraic subject any longer in a sense that the framework today I'd like to share from today you might never think about this way before. So, in my point of view, so of course I can talk about many like the like the philosophical, like the perspective. In my opinion, truth be told, this is just nothing but the integration. I mean, in calculus. Seriously. So this is the key, like the theme and the philosophy I'd like to address in my turn of the presentation. And what I only require is whether or not you know either this one or like this one. So if this is certain like the differential form. This is all I will require in a sense that I will just try to make everything very precise and very concrete. So please do not worry about it. So first, let us just kind of make the critique of two previous presentations from the wonderful two mathematicians. So let me first like stop to share for a moment. So if you just look at the record again, so I completely agree. The topics are fancy, it's cool. So the topic itself is important, and the tools what people here are using is astonishing. I agree. But if you just look at the two presentations again, there is no single picture except isogeny torsion graph. So even we are talking about the distribution, there was no single elementary picture. So this is one like the critique I'd like to make. So if it is possible to like to address the intuition in terms of the elementary like the figure, it could be beneficial. So let's really just think about what we learned in our middle school in math about mathematics. So when we talk about either the like the linear equation or the like the circle, so you already identify the picture, I mean the graph of certain like the trajectory with the equation. So I want you to think of what was really happening before, in a sense, that so if you just draw, okay. So in our like the middle school life, we like this. And then we also like the circle. We like this. And even I draw such a like the simple like the circle, we know how to parameterize in terms of certain equation. We know that pretty well. And we also know how to draw the line, circle. So what we did before is that, well, then it overlap with 2 points, then we know how to capture them by using algebra. That's the way we use both algebra and geometry. I will not talk about anything detailed because all of the participants here are I assume you know how to teach this for the undergraduate. So either the algebra or geometry, I want you to think about your perspective. You are actually using both of even you just solve two equations, you solve that's a discriminant, but you are actually imagining the picture. and you just try to identify those are actually the same. So we'd like to say algebraic geometry is the way we did in the middle school. So that we already draw the picture, but you know how to identify that picture with certain algebraic structure, and then you'd like to take the benefit from there. So that's the way to do it. Then first, when we talk about mathematics, so what is mathematics? So of course, it's kind of the like a heuristic, like the way to address. So mathematics is learn what is the set with the function. And of course, we'd like to generalize this as a certain like the class and function as a certain like the morphism and functor and so on and so on. Because we know so the collection of the certain like the objects is no longer the set we know it. So mathematically speaking, we should talk about the proper like the class and the morphism, those kind of things, rigorously speaking. But the reality, we want to just talk about the collection and the way to just map from one to the other. That's all we care. So mathematics, whatever subject we care, is just about learning what is the set and what is the function. Linear algebra, vector space with linear transformation, topology, topological space with the continuous map, and so on and so on. Basically, elliptic curve, yeah. So elliptic like a curve with a certain reason like the algebraic morphism. So then, if you just look at this like the elementary example, the set is certain like the zero locus, zero set of polynomial. So this is what we'd like to say certain algebraic set. So because we are huge fan, big fan of the algebra, so that in the like the algebraic world, when we concern the set with the function, the set we care from our middle school life was such a like the set described as a zero set of certain polynomial. Of course, we can talk about the all other possible like the sets for sure, but in the algebraic world, this is something very reasonable. Is that kind of okay with us? So, for example, that's why when we talk about the elliptic curve, why we like this? Because we know the equation. So that this is written as y cubed equals x cubed plus ax plus b. This a and b are some from some like a reasonable field. Basically, why we like this? Because we know the equation, but still we know how to identify this with certain like a geometric like the intuition. So in that sense, this is consistency with the like the drawing the like the circle and the line. Is that kind of okay with us? Then what is the function? So I'd like to say something very silly. So let's just look at the like the I'd like to, this is the question for you. So most elementary object in abstract algebra. Of course, your opinion could be completely different from the others. I know it. But if you just want to pick up one single object that you'd like to claim, what is the most simplest? Do you have any claim and your own like the reason why you pick this like the object and why you feel this is most like the simplest? But I want to be very like a very like concrete object. So can you just pick up one very concrete like the example that you'd like to, this is simplest. Of course, let's just ignore identity group. So identity like the group is, I don't want to care. So something interesting.
Cyclic group.
Yeah, secret group is one reasonable like the component to generate the group theory. I completely agree with that. That's true. What else? There's no concrete answer. So is there anyone want to try? In my opinion, the most like the simplest one is this guy. Probably this is simplest. And actually, I'd like to give this like the ring to be the complex so that this is sort of simplest. Of course, there should be many reasons. So if you're writing your paper with this single object and you have tons of like a paragraphs, you'd like to say something. So, but let's just think about this in the very like the elementary way. What is this set? This is the collection of the C coefficient polynomial with the one indeterminate, one variable. So of course, this is polynomial, C polynomial. But let's just equip with this perspective, this perspective. So each of the polynomial is a function. This is or certain functions a certain like the, let me say, let me say, certain algebraic functions. So here is what I'd like to say. So when we talk about algebra, of course, algebra, we can talk about the group, we can talk about the ring, we can talk about the field, we can talk about the vector space, we can talk about the module, we can talk about the algebra for sure. But the slogan I'd like to talk about is this is the collection. When you enjoy the algebraic structure, you actually collect something. What is vector space? Collection of vectors. Then it equips with the two operations, right? So collection of what here I'd like to make you be a little bit biased is collection of functions. What is the vector? Vector itself is a function. What is the group? Of course, you might have a different opinion. You might have different like the interpretation. I agree with that. But at the same, very like the juristically speaking, when you think about the algebraic structure, what is the way to do it? We first collect everything. Then it admits certain algebraic structure. But instead of just regarding there's a collection of the elements, I'd like to say this is a collection of the functions. With this perspective, if you just imagine C of x, the very like the simplest possible like the polynomial ring, each polynomials are the functions for sure. Is that okay with you? And then now let's try to look at the number theory because today's like a goal is the algebraic geometry for the number theories. So now you can see something very astonishing from this point of view. So let me now draw the table. So this is the word of CX. So this is sort of the analytic word I'd like to say because we prefer to use C in the like the either the complex analysis or the complex algebraic geometry, and we know how powerful to use complex field from the fundamental theory of the algebra and so on and so on. But in the number theory world, we'd like to use either the finite field or the number field. So the like the baseline, we start from the Z. And then we take the quotient field to get the Q. And then we'd like to get either the number field or the finite field, depending on the context. So with the parallel, like the comparison, I'd like to put the word of Z. So the right side is the number theory word. The left side is sort of the overlap, but it's also from algebra, like the point of it, it makes sense, but still there is a certain like the difference compared to just a Z. So first perspective, this is a collection of reasonable functions. So everything I'm talking about is heuristic that you can completely ignore. I'm okay with it, but still this could be helpful. Then what I'd like to say is that this must be the same so that can we regard this is actually the same. So as long as if you just pick one element from C bracket of X, then you regard polynomial, well, we can regard it as a function. Why not? Then if you take the analog to Z, Z is clearly just a collection of the integers, right? Then as of just a ring, those are sort of the simplest possible rings for sure. But if you regard polynomial ring as a collection of the certain reasonable functions, then why not for Z? And Z is our like, very like the first like the point. In order to like to crush this like the perspective, let me just give you one example. So let's just try to make some observation. And if you have any like questions or comments, because I'd like to share my kind of the very stupid inspiration, you can complete it against it. I'm completely okay with it. But still, I just want to make this like the conversation. So observation. Let's just start from here. Then we know how to write it. So for example, this should be written as A naught plus A1x. And it should be over with the finite like the step. We know this. And we know each like the coefficient is C. This is why we put C here. So it's very like a stupid like a thing to say. But if you regard this as a function, then we know the definition of the function. We need to specify the domain and the codomain and the way to assign for each of the inputs. So this guy, then now your turn. What is the domain and what is the codomain? What is the domain?
Set of complex numbers.
I'd like to be very like the specific regarding each like the set. What is the set of the domain? Because there should be one answer, right?
Sorry, could you repeat the question? I couldn't hear it.
I'd like to specify each of the sets of the domain and the codomain. If we regard f of x as a function, right? What is the domain in your opinion? So there could be many possible like the options, but there's a one single like a very natural choice of the both domain and the codomain.
Wait, I said complex set of complex numbers, and you
Ah,
say
yeah,
this name
set of the complex
included.
numbers. Okay, yeah,
Ah,
that's
yeah.
yeah. I think this is reasonable. Yeah, next one. What about the codomain?
This is also C. The
Yeah,
com
this is simplest. So this must be reasonable choice. So if you just plug in any like the complex value alpha, then it determines f of alpha as a complex value. Is that okay with you? So I'd like to play the same game with z. So this is the analog, and I'd like to make the space, I mean here, so that I'd like to write something over here. So now let's just give you z. Then still I'd like to pick one element. Of course, this is just a integer such as a 1, 2, 3, 17, prime numbers, so on. So that, of course, we cannot write like this, but still I'd like to play the same game. But it doesn't make sense in a sense that c of x, we have some already like a natural, like the way to interpret as a function, whereas z is sort of difficult to do it. So in order to match this interpretation, let's just relook at this perspective again. What was really happening from the algebraic point of view. So when we learn ring theory from the baby algebra, abstract algebra, what is the king of the ring theory? Prime ideas, maximal ideas. And for C of X, we know we do not need to distinguish in a sense that this is PID. I also, all of you know it, so that we don't need to at least distinguish in this like a case, like the for the PID, like the domain, this is a very something nice. So what I'd like to reinterpret this guy is the following. Instead of thinking we plug in alpha to the f of alpha, so once you have alpha, then what you can create is this guy, x minus alpha. Then you can generate the ideal from this generator. Then you can create the ideal. Is that okay with you? Then this is clearly just a reasonable idea in C of x. Then what we can do is we can take the quotient. Agree? We can take the quotient, and I don't think I need to explain anything here that this is isomorphic to C of alpha. Hopefully this is very clear. Then this is also clear that this is equal to C, because alpha is one of the complex values. So if you add alpha, it's just the same as a complex field. Then with this perspective, so what we are really doing is the following. So let me just put this a little bit below. So this was what really was happening. So if you just take alpha, then what you do is you just reinterpret everything in C of, so let me just write like this here, because this exactly corresponds to f of alpha. Then I'd like to just reinterpret this codomain in a sense that because this is just a field depending on alpha, so I'd like to take the disjoint union of all those choices, even though each of the single pieces are isomorphic to C. So the disjoint union of C is kind of just stupid to say, but the rigorously speaking, we just take that as a disjoint union of all those like the parts of like the C of like the alpha. Does that kind of make sense of you? And with this like a structure, what you can realize is that the way to choose this one is actually coming from this one. This is the maximal ideal. because it creates the field. Or of course, you can regard this as a prime idea. That also works. Then what was really happening is that actually what we did here is that we start from here and then we just choose either prime idea or maximal idea. And you took the quotient of it to make the field. And then you just look at the embedded like the image. That's the way we view this f as a function. So with this perspective, now you can realize the following. So with z, we know what are the prime ideas. So the prime ideas in z, this guy is just what? Pz, p prime, union with 0. So in the fancy, like the algebraic geometry term, this is usually written by spec of z. This is a common notation. So spec of z is the collection consists of prime ideas of the given ring. So that I'd like to put this into the domain. As we just put, actually not just the alpha, but the maximal or the prime idea generated from x minus alpha, we are playing the same game. Then you choose one of the prime idea, p, prime idea. Then what we do is we just choose z quotient out by p. So if this was pz, then it becomes the field that satisfies with the previous observation. But if it quotient out by 0, so still this is nothing but the integral domain. So we just want to make it to be the quotient field and just look at the corresponding image. This was exactly the way to look at f of alpha in the C of x. So the corresponding codomain is we just choose all possible prime ideas. And then we take the disjoint union of the quotient, like the field of this, like the quotient, like the ring. So in that sense, we can really regard each of the integers as a function as we regard each of the element of the polynomial ring as a function. So with this perspective, let's just give you this like a point. So for example, if you have like this 3, what is 3 as a function? Then I'd like to say, then let's just start from spec of z. So that you just take, for example, pz, for example, let's just take 2z. Then what you make is just take the quotient. Take the quotient. Then just look at the corresponding just image. Then we know what this is. This is 1. And if you just choose like the 0, of course 0z, then this is just the same as just this guy. It's stupid to say it. It's just the same as just a z. So in that case, we just look same, just a 3. But by taking the quotient space, sorry, the quotient field, so this just becomes q. So it still makes sense of talking about the like the 3, so that we just take the disjoint union of it. So that indeed we are able to view each of the integers as a function as we observe the polynomial ring like that. So this is a very first important point of view from algebraic geometry to view algebraic like number theory or even analytic number theory for sure in a geometric point of view. So the very like the first like the point of view I want you to appreciate is that when you think about the z, then what is z? It is the collection of the functions, as we regard C of x as a collection of the functions as well. This is a very like the first like the point that some of you might not never actually think about this before. So if you want to just study this perspective, you can just look at the Adia McDonald quantitative algebra, like the textbook, especially like the exercises in the chapter 1 and chapter 2. So those are the content what I'm now currently talking about. But the desire is to view Z as a same analog from the C of X. That's the point of view. So if there are any questions, just let me know. So because this is not kind of the lecture, but I just want to share the way to view from algebraic geometry point of view. Then now you can see something a little bit weird if you think about Q with this perspective. So let's just take the quotient field. The quotient field. So now still I just want to view. Still this is the collection of functions. But rigorously speaking, in the algebraic geometry textbook, this is usually said by so-called sections. So actually they are the same. I just use the term by the function because function is more like the intuitive. But rigorously speaking, this is called by the section of the structure like a shape or whatsoever. So each of this guy is coming from spec of Z that maps to disjoint union of the quotient field. This guy. Yeah, so if you have any questions or comments, just feel free to stop what I'm doing. So now let's just look at the quotient field, which is Q. What is Q? We know what this is. It's very clear. But as now you equip with the perspective that Z is a collection of the function, so that there should be a certain the perspective on Q as well. And Q is probably the most important object in number theory for sure. So if you just take the pullback of the perspective to C of that's a polynomial ring, then what we care here is what? This guy, C round of X. Usually this is called by the so-called function field. But let's just do not think about anything in the the language way. So let's just think about the concrete the object, what was really happening. What is this guy? So this is the object written as f of x over g of x, where this g is not zero. It's clear. So that what is this? We learned this from in my the memory from the middle school. So rational functions. So here I'd like to put the color that you really view this as a function before, right? With the reasonable choice of the coefficient. So let me just repeat. So algebraically speaking, you just take the quotient the field, which is the smallest field containing the chosen the ring. We know the algebraic the definition, but what you create from the polynomial ring was that you just actually make the collection of the rational functions. And in complex analysis, this is usually said meromorphic functions, but they're actually really the same. So I want you to now imagine, then what is Q?
Should be the set of rational functions again.
Rational functions. Because if you now think of the definition, such as A over B, where A is not zero, what was A and B? Those are the functions. From the description I already gave you, and we just took that just a rational function. So here, this is the one single the slogan I want you to take. What I said in this the page, what is algebra? Algebra is the collection of functions. Whatever structures, either the group, ring, field, module, vector space, algebra, whatever structure, algebraic structure you consider, I assume you feel familiar with the way to generate the algebraic structure, collect everything that you care, then it admits or enjoys certain the algebraic structure, and I'd like to say collection of what? Actually what you really collect was the functions. Depending on the interpretations for sure, but this is the way to interpret in geometric way. So mathematics is about studying set with the function. What is the algebraic theory? Algebraic theory is we start from the set and then we collect the functions. That collection admits certain algebraic structure. So this is the algebraic geometric point of view. This is the first thing I today want to explain. So any questions or comments?
Yes, I'm just trying to imagine this like a Q as a set of rational functions. So for example, if you choose 1 over 2, then you're gonna evaluate spec Z at 1 over 2 for many ways. So just bring any s- prime ideal into spec Z and evaluate at 1, evaluate at 2, and you take the ratio.
Yep.
But what happens to when you pick like a
So
prime
if you
2 as an
look at
ideal?
the codomain that we just declared, so for each of the prime or the maximal ideals, we already made the quotient field so that the or actually you
Gunhei,
are talking about makes sense.
I think what you want to say is field of fractions.
Yeah, field of the fractions. Yeah, quotient field or field of fractions. Yeah, thanks for the like the clarification. Yeah, so already the all those operations were already declared in this like the level of the codomain, so it makes sense of like talking about the rational function in this level. And if you imagine further, even I just said everything with these concrete two examples. So as we have two non-trivial examples, we know this works for infinitely many examples. So if you just replace C of the polynomial ring with Z, you can just replace it by commutative ring with 1. Then we know from Jones' lemma, maximal ideal always exists, at least one, and the maximal ideal is always prime ideal. So that it makes sense of talking about the spec of the given arbitrarily commutative ring with identity, you can do the exact same game here. So in that class of the any commutative ring with 1, you can play exactly the same game in a sense that you can always talking about each element as a function. And then by taking either the fraction field or the quotient field or the localization that I eventually want to explain, so we can actually really generate the rational functions for the given ring. In that sense, this also works for the finite field and the number field as well. Because as long as we have a commutative ring with 1, this like the observation can be extended in the same way. That's one story.
Oh, so my question is, what if you choose 1 over 2, and how is 1 over 2? How do you like to define the evaluation of 1 over 2 at the prime 2 ideal, for example?
Yeah, so this is the way to think of in this way. So if you have, say, f of x over g of x in c of x, right? Then if you just choose alpha, then we know we will assign this to be f of alpha over g of alpha in this way. So that we'd like to just expect the same game in a sense that we just view here f and g as a function from spec of like the c of x to just this guy. Like this. So even we took this like the perspective because we'd like to plug in same alpha. So here alpha is now actually x minus alpha as a maximal idea. So that it makes sense of just talking about the g of alpha and f of alpha in that fraction field. So if you now imagine with like the z, now you have a q, then now you have a over b. Then still you have the same perspective. Like this. Then if you just pick this alpha, then it makes sense of talking about the AOP over BOP in that fraction field. So the way to work is exactly, it should be exactly same with the polynomial ring. So in that sense, what is algebraic geometry? Algebraic geometry is studying polynomial ring. And the slogan is actually the commutative ring with 1 is actually same as the polynomial ring in this perspective. So this is why this perspective could be beneficial to study number theory in a sense that when we look at the number field, finite field, this is very abstract and it's very hard to digest the intuition. Of course, the logically like the flow can be also very challenging for sure. But the way to view this like the algebraic object is that there's just given like the spec of the R, which is a reasonable topological space. Then we just collect the functions then we know how to track the picture with this like the point of view by just looking at the polynomial ring. So this is algebraic geometry perspective. Yeah, feel free to like interrupt or just share your imagination if you have the perspective for any. And it is important to thereby look at C of X in our like the first place because C of X we know how to deal with it without using any heavy machinery. And this like give us the guidance how to algebraically generalize the geometric concept to the very like the abstract like the algebraic world. So polynomial ring is always the not only the starting point and also the last like the perspective we'd like to understand. Algebraic geometry is to just study and understand polynomial ring, what was really happening. So if there are no other questions, let me continue. So here is one important like perspective.
Just one more question, sorry. So you say we can play this kind of game as long as you can define the maximal ideal or prime ideal. So in general case, because in this case maximal ideals are prime ideals, but in general, like a ring, do we need to work on the M spec or just simply spec?
Yeah, thanks for that question. Now let me just try to distinguish the word of geometry to give you the answer you back. So I assume you never heard this like this story before. If you never worked with the analytic geometers before, so the first like the important like the point of view that you need to know is what we care is actually the calculus. So if you look at the compact orientable surface in R3, let's just look at the undergraduate mathematics again. So we learn this type of objects such as like the two-dimensional sphere or the like a torus in like the multi-variable calculus class. We learned this. So first, this is important to know. This is algebraic curve. So let me give you two examples how this works. So for example, if you look at sphere, this sphere is same as CP1. I know some of you might need to think about why they are exactly the same, but if you just look at review the definition of projective space first, and if you just apply this for the one-dimensional case, these are exact same by just it follows from the stereographic projection. Okay, so you can just really just view this as the same. In algebraic geometry, this is usually called by the rational curve. So each of the point, it has two tuples, basically two tuples. Then what you can do is you can embed this guy, for example, into CP2 in a way that for two like the components here, you can just map to x squared, xy, y squared, like this. Then you can show this map is embedding. You can show this map is embedding. And if you just take the coordinate as capital X, capital Y, and capital Z, capital Z like this, you can see the relation is described as x squared times y squared equals xy squared. So the image CP1 is same as the image under this map. Then this map is the zero set of xz minus y squared. Now let's look at the torus. What is torus? We actually need to say many things here, but it is homeomorphic to S1 cross S1. This is the definition of the torus. So as you know from your experience, there are infinitely many elliptic curves, and we identify elliptic curves topologically as a torus. So even topologically same as S1 cross S1 does not mean that they are the same actual torus because it automates an additional structure. But anyhow, the definition of torus is the surface homeomorphic to S1 cross S1. So what you can imagine is like this, intuitively very clear, just a donut, so that you have a one S1, and another S1. So that S1 cross S1 gives a torus for sure. So this is a compact surface. So what was the algebra, as I said, collection of the functions. So what we want to just collect is the function defined on the torus. Then it turns out that this, like, first of all, S1 cross S1 becomes R2 quotient by so-called lattice group. And I should learn this, like, the structure from the experts here. But yeah, anyhow, this is kind of clear. So intuitively, you have this as R2, and you make the lattice group such as like this. And we know how to define the equivalence class, like the relations, and we know how to identify. So that's the way to just make the torus like this. So because of that, the reserved functions, and let me say holomorphic. Let me say rational. So because some of you might not like complex analysis, let me say rational functions on S1 cross S1. So if you just look at this guy, so if you start from the rational function, if you add them, still that should be the rational function. If you multiply, should be the rational function. With the non-zero, like the rational function, you can divide by it. So this becomes a field. So this is so-called the quotient, like the function field. And it is known by bias stress. This is generated by C adding by two elements with the two generators, P with P prime. Here, this P is a so-called bias P function. This guy is written as 1 over z squared plus lattice point with, if I remember it correctly, is something like this. So this is pole of degree 2. And P prime thereby is pole of degree 3. And bias stress proved this, like the function field is generated by P and P prime. And furthermore, so now let us just start from this torus S1 cross S1. So that let's just take this, like the perspective from C cross C, because S1 is sit inside of C1. Is that okay with you? So circle, e to the IT is the subset inside of the complex plane. So S1 cross S1 is clearly is just inside of the C2. Then if you just take the element from here, let me simply just call it by Z. Then what I will do is I'd like to map this guy by P of Z with P prime of Z, so that you can see that I actually map this guy to C2, because P and P prime are complex valued functions. Then in fact, this is just some open subset inside of the CP2. And this map is also embedding. Then if you just write down this embedding, so can you guess what this should be? So this guy is a zero set of P prime squared equals P of Z cube plus A PZ plus B. Here AB depend on the lattice. So this was the bias equation, elliptic curve equation. So the reality of the elliptic curve is that you start from the torus, then you embed this to CP2, then this image is the elliptic curve. Then why it admits the abelian variety, like the group structure? Because S1 is abelian group, for sure, S1. S1, right, e to the IT, collection of e to the IT, so it is a group, for sure. It has admits the identity element, so with respect to the natural, like multiplication, it is a group. S1 cross S1 per group. So it's a abelian group for sure. We embed, so it does not change any, like the structure, thereby it should be the abelian group. So this is the reason why elliptic curve becomes the abelian group. This is like the way to define the associative law with the abelian group structure is indeed coming from S1 cross S1. And I'd like to go further a little bit. So this is now our geometric perspective. So why we always draw elliptic curve, something like this. Of course, there's a singular one, I know it. So like this, I know it. So can you guess why we always draw elliptic curve like that? What is the elliptic curve? It is the image of the torus inside the CP2. Then when we talk about the curve, so this guy, when we embed them, then all we just look at is just a real part. So let me now share the common like the elliptic curve, like the figure that you know very well, probably more than me. So for example, if I just share the Google like the search, this is what you feel very friendly with you. Can you see? We actually look at the torus and just project down to the real part. That's why it looks like something like this. So it is coming from the torus. Torus, you embed that in CP2, and or we can just look at this as either the two-dimensional or three-dimensional like the perspective, because we are human being, we cannot go anything beyond. So all we just do is, because now if I just reshare this kind. So as you know, we just replace this p by x and p prime by y, so that this is nothing but x comma y in C2, satisfying y squared equals x cubed plus ax plus b. So this is a complex like the pair satisfying one equation, so that all we just do is we just look at the real part image of x and y, satisfying this equation. That becomes the usual like the picture of the elliptic curve. So because we ignore the imaginary part, that's why it looks like the curve. That's why we call it by the curve. But it doesn't make sense. Why we can really say elliptic curve is same as the torus. Torus has a surface, whereas elliptic curve is a curve. How the curve can be same as the surface? That doesn't make sense because we only look at the real part. So that's why it looks like something like this. It looks like completely disconnected. How the torus can be disconnected? That doesn't make sense at all. We just look at just a one like a perspective of the single like the piece of the like the torus. That's what was really happening. So from here, what I wanna say is that all our algebraic structure were really coming from certain like the geometric like the figure, and there should be some geometric understanding of what was really happening before, in a sense that we can even view z and q as of functions, and the torus or the elliptic curve is one reasonable object, then we can play both of the perspective at the same time. So let me just repeat. We can either, over the like the complex field, we can either use classical calculus to understand the torus, or we can just look at the elliptic curve with just putting the algebraic, just leaving the algebraic structure. But actually, we are talking not different like the structure. We are actually talking the same, but we just use a different like the tools. So the way to study Z, Q, number field, finite field in algebraic geometry perspective is we first look at the C of X polynomial ring and equate with the algebraic, like the geometry, like the understanding first, and then try to apply into this like the algebraic world. And the elliptic curve and the complex torus is a very good example to equip this perspective. So, and people really enjoy. That's why elliptic curve is a still central object in number theory, in my understanding. So therefore, what I'd like to do in this seminar, in my turn of the presentation, is I'd like to reinterpret what two number theories like the presentation in purely classical like the calculus perspective. So here's a way to do this. So if any of you just think, so if you think about the like the elliptic curve over a finite field, let me say f of q, then you know this guy is the collection of the pairs here satisfying this equation. for some AB. You know this, and you already know this is a finite set, or in some cases this is just a finite. If you just like to take the finite vector field, then what we do is we just take the field extension behind, take the field extension to what? From f of q to c. Then what we create is elliptic curve over c. Why we do that? Because now we recover the complex torus, S1 cross S1. Then we know how to understand it completely in the geometric way. And then we apply that perspective to the list as finite, like the subset, over the either the finite field or the over the like the number field. So in that sense, there's a way to just interchange from one to the other. That's what I'd like to do. So yeah, so this is in that sense the number like the algebraic geometry for a number like the theorist in a sense that how we really reinterpret those algebraic structure in this like the sense of the like the understand that like the certain like the figures. Any other comments or questions? This is algebraic geometry in my understanding. So most like the students are very overwhelmed with the just or like the amount of the necessary like the language tracking. I know it, but the reality is actually just understanding the torus.
Could you quickly give some like a general like a strategy how to extend FQ to C?
What I'd like to say is the following. So rather than giving you the mathematical answer, let me just give you very heuristic that you can completely against it. So I should learn from you for such like the pictures. I assume you know those type of the pictures very well. So these are the certain finite set. Those are finite sets. But if we just look at those types of the elliptic curves, those are some like the special points that ask you to study like the torsion, like the points and so on and so on. Those are like the key central object in number theory. I agree with that. But instead of just only looking at those like the finitely many just point from the chosen finite field, if we because we keep the same equation from the Weierstrass equation, if we not plugging into x and y with that finite field, if you just replace it by c, then it becomes the continuous, it becomes a torus, right? And because we just preserve the same equation, Weierstrass equation, still we can play the same algebraic like the observation, right? But from the complex like the point of view, so because we know it's coming from indeed the complex torus, then we can just really visualize it, what was really happening for the complex torus. And if you just take this certain subset preserving the algebraic structure, then we can really see what was really happening before. So with this perspective, today I want to just provide one very weird example of the Galois group that you feel very friendly with it, but still. Yeah, so I'd like to today just provide one necessary like the example to like to convince you that what you are really doing in the algebraic way is closely related to the geometric structure. So with that like the heuristic like the answer, let me now search the Galois group. So assume that you saw Galois theory and you saw the statement, the fundamental, like the theorem of the Galois, like the correspondence, that kind of thing, and the Galois representation is the or the central object for the computation using the like the order necessary like the matrices. So if I just search this guy, this guy, so let's get track of what you did before and try to link what I'm today talking about. So first, when I look at Z, the integer like the ring, I always think of C of X, polynomial ring. When I think of Q is analog from the C round of X. Those are both of them are the function field. So now if you just look at this exact like a definition, you might feel a little bit weird. So if you look at this the Galois group, I assume I actually need to learn from the experts here. But if you just look at the definition, so the definition of the Galois group is given by the two fields. So we start from the one like the subfield and we extend to the E, and the Galois group is defined in terms of the automorphisms that preserves F as an identity and it could be changed with this like the extension, like the elements. That's the Galois group. So the mathematical description of the Galois group is very clear. We have the like the subfield and the extension like the of the like the F, E, and then we just look at the Galois like the automorphism. So that preserves this F, but it could be changed over like the E in general. Then such a like a collection makes a group, and that's we call it by the Galois group. And when you look at the examples, including this like the page, we always look at Q and some like the simple extension, and beyond is a very deep theory, as you know. So, so you might so far just think of such a like the examples with the algebraic perspective. Now let's just change the perspective a little bit. What is the field? It's a function field. It's the collection of the rational functions. Already Q is the collection of the rational functions. And we already said if we start from the commutative ring with 1, if we take the fraction field, we have the same perspective. So that it also works for Q of square root of 2, and so on and so on. Then I want you to wonder that what was really happening in the level of the polynomial ring with this definition. I'm not talking about the mathematical rigorously of the like the description here. I'm just saying, so there should be the reason like the picture, which should be very elementary, but at the same time, it should make sense of talking about this definition in that picture. Then first, let's just look at this guy. So this is a base field. So the simplest possible one in the number theory is a Q. I agree with it. So Q. So if you look at the analytic word, what is the analog from Q? C round of X. So instead of looking at the definition, now it's your turn to share your imagination. So C round of X is the collection of rational functions. Then in order to talk about the functions, we should talk about the function defined on certain space. What is that space of the C round of X? What is it? C round of X consists of the rational functions. And what is the space that each of the rational functions are defined? You already know the answer.
Spec C of X.
I agree with that. It's a collection of X minus alpha. You gave us a very completely correct answer, but I just want to say just simply C.
Okay.
Because alpha corresponds to X minus alpha as a maximal idea or the prime idea. But juristically speaking, we can just say just alpha. So each like a complex like a value. So each rational functions are defined over collection of the alpha, which is a complex plane. Complex plane. It's just simple. And each of the element we just regard as a maximal idea or the prime idea. Is that okay with you so far? Next, rational function. Why we care rational function? We care the infinity, the pole. So not just this guy, C, complex plane. We also care the pole, which is the infinity. What is it? CP1. So the reason why we care the rational functions is that the underlying space is actually CP1. So with this perspective, given the field F, I'm not talking about E yet. So let's just think of this F first, because this must be our starting point, right? So if you just take this F as a C round of X, then what is the underlying space? S2. This guy. Now let's look at E, which is the extension of this base field. So now let's also look at the perspective from C bracket of X, C round of X. So this is our chosen F. Is that okay with you? So please give me one reasonable non-trivial extension field from C round of X. What is it? The hint, elliptic curve equation.
You
C,
bring another variable.
X and Y.
Yep. Let me now write it for you so that you will be the same page with all of us. So mathematically speaking, so when we're talking about the Galois group, so rather than just view this by Q, this is what you feel very familiar with it, I know it, but rather than thinking this one, just take this to be C round of X. then you already choose this one. I know it, but rather than thinking this like the very like the important like the algebraic object, let's just take this to be. I'd like to add by another indeterminate variable y. Then I just want to take the quotient by the bias test polynomial. Let me write it for you. Then we took the quotient by for the PID. This is the field. We start from the field, we create the PID, we take the quotient by the maximal idea because prime idea is same as the maximal idea. We know it, so that is a field. So therefore, this is a field. And clearly, this is the F becomes the subfield inside of F, inside of E. Does that kind of make sense of you? So now you should use your own like the bias geometric like the imagination. So when you already choose F, which is C round of X, you are actually really imagining. So yeah, each function, like the function is defined over the like the actually not only complex plane, but with the infinity. So it is actually CP1. When you choose E in this manner, what is this E? What is the underlying space? As you might already know.
Isn't it the torus?
Yeah, elliptic curve. So in that perspective, so when we algebraically pick up this pair E and F, what you really picked, geometrically speaking, is that you picked two spaces, torus, elliptic curve, to the CP1 or the rational curve. So what you really pick are first you pick two underlying spaces from each chosen like the function field. So then again, I'm not saying just of these like the examples to be very special. This works for the arbitrarily commutative ring with one, this perspective. So this perspective definitely works for your world of the number theory, even with the characteristic equals 2. This is very general theory. Even I explain everything with this the analytic word because this gives you intuition without just giving any like heavy like the language. So then we have the like the field extension so that you expect there should be certain like the comparability condition from the between complex torus and S2 or the elliptic curve to the rational curve. Does that make sense of you? So now let me play something that you might like it or dislike it. I don't know it. So what was really happening? So now you have the elliptic curve. We love it. And there's a rational curve. And these are just standard like the terms from algebraic geometry. So if you want to think of this way, you can just think of this as a really the torus, S1 cross S1. So this guy is just nothing but S2. So now here's your turn. Can you make the natural map from either torus to S2 or S2 to torus? Can you do that? Can you make the some reasonable map here? So for that, let me first explain the algebraic description. So what do we know regarding the elliptic curve? We know the equation. And like the corresponding like the field is described in terms of x and y. We know it. So each of the element is described in terms of the pair. Then what is the natural like the assignment? It should be x. Then there are two like the natural choices from the power of 2, order 2. Then we can assign x comma y and x comma negative y to the same element. Algebraically, this is clear because we take y squared. We take y squared. So even we choose the negative y, it maps to the same element for sure. So let me describe everything without using any algebra. So let us start from the torus. You can imagine. So if you have a donut in your like the own like the apartment, just bring it. You have a donut. Then just make the. So let me just find one of the student of enjoying math YouTube channel that I let him make some like the practice for that. So it might take just a minute. Just give me a minute because this visualization could be very helpful for you. Because it's been a while I taught this before, so just give me a sec. And my presentation today should be over in 10 minutes for today. So this is the very like the sloppy introduction regarding algebraic geometry, but hopefully this could be helpful. Just hang on. I shared this to the like the YouTube channel, but it's been a while and there are plenty of different like the notes. Yeah, sorry. So let me just take just one more minute. Sorry for that, because I think this could be very helpful. I think this one. Ah, no, sorry. I'm sorry. Just sorry. Just give me a sec. Sorry. So this is a very important, like the visualization. So I want to share. Oops. While I'm searching the visualization, like the note. So if you have any comments or questions, please let us know. It's hard to find it. Let me just explain just with the word. So just start from the torus, and just take the just the line exactly center under like the torus, just to make this kind of thing, and just give the equivalent relation in a sense that if you rotate exactly 180-degree, rotating via this like the line, and if it go back to the original like the point, we will say it has a relation. Then you already have the donut. Then you just take the stick exactly in the center and just rotate 180-degree. Then you can see that there are four fixed points for sure. And then we will identify each of the 2 points because once we rotate, we will say they are related. Then just take the quotient set from there. Then can you imagine how it look like? So if you just take this quotient set from this equivalent relation, then first you just take the slice to make the donuts to half first, so that you make the like the donuts like this, just half. But still, you should identify this like the two circles in each, without except these two like the four like the fixed points. Then if you just take just glue them because from the identification. So can you imagine it really topologically look like the two-dimensional sphere? Can you kind of imagine? Start from the donuts. And so this is a visualization I'd like to share because some of my students did this like the visualization very concretely in the one of the like the class in the YouTube, yeah, enjoying my YouTube channel. So that just you take just half of the donuts and then still you should just glue like the above and the below, except this like the four fixed point. If you glue them, then if you think of this as a homeomorphic way, then this exactly becomes a two-dimensional sphere. So the algebraic like the map in algebraic geometry, this map is called so-called the involution, meaning that if you start from the so-called the abelian variety, you just take the relation by x is related by negative x, then this guy becomes the rational curve. And the topological description I gave is exactly correspond to what I explained this like the algebraic like the map. So the Galois like the group is indeed coming from this like the so-called the 2-to-1 branch covering. So conversely, this is like the geometric point of view of the Galois extension. So given Galois extension, then actually there's a corresponding branch covering from underlying two underlying spaces. I'm not saying this works over C. I'm saying as long as you rig over the commutative ring with one and it's like either the localization or the fraction field, this geometric interpretation is not the analog. This is exactly correct interpretation that works for the algebraic word. So that works for the number two. And in this perspective, so this is the way to identify the certain like the differential form with the L function in the number theory. So L function, the modular the curve or those kind of thing are indeed coming from the calculus word, because there's a way to use the classical calculus differential form to interpret how we really obtain such like the algebra like the objects. And this is I'd like to explain in my like the turn of the presentation. So there's a like the isogeny so there are like the purely like the heavy algebraic like the concepts that two experts want to explain, and I'd like to reinterpret in terms of these types of the perspective. Then it does not require many like the prerequisite or the knowledge, in a sense that the objects are very like the concrete. So yeah, but yeah, I first want to just give you the motivation why we kind of like feel this could be interesting or kind of the beneficial. And yeah, the reason I want to, this is my last comment for today. So the reason I want to just explain this perspective was that, so Geran concerned the extension of his like the classifying those like the graphs with this perspective. So that it's very clear point of view that you can really interpret everything in terms of the like the or understand the like the complex like the torus, then you can apply it. And I believe what John represented last time is also closely related. So I'd like to just throw this type of the very stupid like the pictures that could be at least fun, and this could be beneficial for the students. So that's all for today. And sorry for very like the messy like the conversation and also the note. I will share this note to John, so John can just share this to the others, but this might not be very useful. And I kind of expect that this is not the lecture style, but also just a conversation, so that if you just express what you really like the feels or how you really like the understand. So if you just share it, then I'll try to reflect. So this is not just yeah. So I like that types of the conversation because I don't know anything, truth be told. So I just try to make everything very precise. So, but in this like the context of the like understand everything like the pictures. I like this. So yeah, if there are any questions or comments, let me know.
I like this talk.
Yep. Thank you very much for the talk.
Okay. Yeah, thanks for saying that. Okay, then could be better to just stop the record and we can continue to talk.